Welcome everyone. In the previous video, we studied about the phenomena of refraction, which is when light travels from one optical medium enters into another optical medium. Then at the interface, it changes its path or it bends. We also learned about the cause of this refraction, which is difference in the speed of light in two media. If the difference in the speeds is more, then there will be more bending. And if the difference in the speed of two media is less, then less bending will occur. Today we will learn to measure this extent of bending, and that physical quantity which measures this bending is called as refractive index, and we define it as the extent of bending of light when it passes from one optical medium to another. We divide refractive index into two types: absolute refractive index and relative refractive index. Absolute refractive index is calculated when we compare a medium directly with the vacuum. Means if light traveling through vacuum enters a medium, let's say water, then how much is the difference in the speed of light into media, or how much bending will occur in water, will give us the refractive index of water. Similarly, if light is entering from vacuum directly into the glass, then the extent of bending in glass will give us the absolute refractive index of glass. So we define absolute refractive index as the ratio of speed of light in vacuum to the speed of light in the medium, and we denote absolute refractive index with the symbol n or mu. For speed of light in vacuum we use c, and v is used for the speed of light in a medium. Thus the formula for absolute refractive index is n is equal to c upon v. So now we have understood from this formula that refractive index is inversely proportional to speed of light in a medium, which means that if one increases, other will decrease. So we understand that if a medium has more refractive index, it means its optical density is more, which means bending of light will also be more, but speed of light in that medium will be lesser. The factors on which this absolute refractive index depends are nature of material of the medium, wavelength or color of light, and temperature. So let's first see nature of material of the medium. Now here there are two different media. We see that in this case bending is less, means refractive index of this medium is lesser. Here bending is more, refractive index of this medium is more. So different optical media have different refractive index. So first factor is depends upon the nature of the material. Second factor, refractive index also depends upon the wavelength of light. In the previous video we have studied this part in detail, that white colored ray of sun is made up of 7 colors, and all these 7 colors have different wavelengths. Out of those, red color has maximum wavelength while violet has the minimum wavelength. As a result, red color shows minimum bending and violet color shows maximum bending. Now consider these 7 rays. They are traveling through a medium and all the 7 rays are entering into the same medium. But red color is bending less while violet color is bending more, which means that the same medium has lesser refractive index for red but higher refractive index for violet color. So if you want to know more about this, please refer to my video about refraction of light. Now one more thing here we need to understand. We have seen that red color shows minimum bending, violet color shows maximum bending. Now notice the angle of refraction for both of these rays. We can see that in case of red color, angle of refraction is larger, while in case of violet, angle of refraction is smaller. Let's make a mind map here. Consider only the red colored ray. If there is less bending, means there is less refractive index, which means the speed of light is more, and in all the 3 cases, angle of refraction will be larger. So we can relate angle of refraction with these 3 things. Remember this clearly because it is going to help us in solving some problems related to the refractive index. The third factor on which refractive index depends is temperature. So more the temperature, faster the rays will travel. As a result, lesser will be the refractive index. Second type of refractive index is relative refractive index, and it is calculated when light traveling in one optical medium enters into another optical medium. Here we compare the absolute refractive index of the two media and find out how much bending will take place. So we define relative refractive index as the refractive index of one medium with respect to other. Let's see this figure first of all. This is medium 1 and this is medium 2. Incident ray traveling from medium 1 enters into the medium 2. Now we need to see in which medium refracted ray is present. So here refracted ray is present in medium 2. That is why we will be able to find the relative refractive index of medium 2 with respect to 1. So we can find the relative refractive index of that medium in which refracted ray is present. So according to this, now we will find refractive index of medium 2 with respect to 1, and it can be written in these two ways and both will be read in the same manner. Refractive index of medium 2 with respect to 1, and it will be equal to absolute refractive index of medium 2 divided by absolute refractive index of medium 1. Remember, whenever we are writing refractive index, we are referring to absolute refractive index only. Thus the formula now is refractive index of medium 2 with respect to 1 will be equal to n2 upon n1, and we have just seen that n1 will be equal to speed of light in vacuum divided by speed of light in medium 1, and n2 will be equal to speed of light in vacuum divided by speed of light in medium 2. If we replace or insert the values of n2 and n1 in this formula, c and c will get cancelled and will get v1 upon v2. So now our formula for relative refractive index becomes refractive index of medium 2 with respect to 1 is equal to n2 upon n1. It is also equal to v1 upon v2. So it means that this relative refractive index can be found in terms of their absolute refractive index also, and in terms of speed of light in the two media also. So we have just seen that if refracted ray is in medium 2, we find refractive index of medium 2 with respect to 1. But if refracted ray is in medium 1, now in this figure we can see that refracted ray is in medium 1. Now we will find refracted index of medium 1 with respect to 2. So it will be equal to refractive index of medium 1 divided by refractive index of medium 2, which will also be equal to v2 upon v1. We need to pay attention to one thing. Here n1 is above but v2 is in the numerator. Here n2 and v1 are in the numerator. So you need to notice this thing carefully. So now we have seen refractive index of 2 with respect to 1 is this. Refractive index of 1 with respect to 2 is this. If we find the product of these two here, we can find the product in two ways, either in terms of their refractive indices or in terms of their speeds of light. So in both the cases, product will come equal to 1. If we take this on other side of the equal to sign, now we get refractive index of medium 2 with respect to 1 will be equal to inverse of refractive index of medium 1 with respect to 2. Now this is the mathematical formula whose application is that if a ray of light is passing from one medium and enters into another medium and follows some path, if we reverse the direction of this ray on entering the first media, it will exactly follow the same path. This is called as principle of reversibility, and we define it as light will follow exactly the same path if its direction of travel is reversed, and mathematically this formula is the principle of reversibility. We will now see the laws of refraction of light, and there are two laws. First law says incident ray, refracted ray and normal at the interface at the point of incidence all lie along the same plane. Now first of all, notice that I have used 4 different colors to write this law, because whenever you write the law you need to specify all the 4 points. Let's understand what is the meaning of being in the same plane. Now let's say these are the 3 people who are lying along an incident ray, a normal and a refracted ray, which I have drawn on the floor. So all 3 people are lying flat on these 3 rays, so they are all along the plane of the floor. Now if one of them gets up and stands up on the floor, now this person is at right angles to the plane of the floor. So the plane of the 3 does not remain same. And to obey the laws of refraction, their plane should be same. So I hope you have understood what is the meaning of a plane. Okay, now come to the second law. Let's understand the second law with the help of this figure. N1 is the refractive index of first medium and this is angle of incidence. N2 is the refractive index of second medium and this is angle of refraction in this medium. Now this law says that refractive index of first medium multiplied by sine of angle of incidence will always be equal to refractive index of second medium multiplied by sine of angle of refraction. If we bring the sine terms on one side and refractive index on the other side, now this formula will become like this. Sin I upon sin r will be equal to n2 upon n1, and we have just seen that n2 upon n1 is the relative refractive index of medium 2 with respect to medium 1. We can also say that second law of refraction is the ratio of sine of angle of incidence to sine of angle of refraction, and this ratio is always constant. And we can state this law as the ratio of sine of angle of incidence to sine of angle of refraction is constant for a given pair of media, and this law is also called as Snell's law. Now Snell's law is applicable under 2 conditions. First is when the pair of media remains same. Means if we have taken, let's say, air and water and we keep on changing angle of incidence, then sine of angle of incidence and sine of angle of refraction will always remain constant. By changing I, R will also change so that this ratio remains constant all the time. But now if we change the pair, instead of water now we take air and glass. Still the ratio remain constant, but this constant value will be different from the constant value of air and water. So we can say that this law is applicable, or this value will be constant for a given pair of media. Second condition under which Snell's law is applicable is angle of incidence should be greater than 0, but it should be less than 90 degree. Remember that the constant value in Snell's law is equal to the relative refractive index of 2 media. And that is all for today. In the next video, I'll talk about the phenomena of refraction and its applications and the technique to draw their diagrams. If you have liked the video and you want to see more such videos, please click on the subscribe button. Thank you.